Welcome to Project Fhelix. My name is Irving Polanco. It is currently the May 2026 term in ENGR 404 Mechatronics. This is the final project. Most people who want to get a pet are usually shocked by how much responsibility it takes to actually take care of one. I included this image for a reason. There's many points where owning a pet is more than someone really bargained for, and cats especially. Pets can be messy, and not all families can afford the responsibility. When some people get pets too, it feels like they're getting another child, but this child doesn't learn and it never grows up. So, as a robotics enthusiast and a mechatronics student, I undertook the project of creating my own pet. And this kind of pet will require less responsibility. It will give more enjoyment to those who own this pet because it will not make messes. It will be low maintenance and still maintain that emotional engagement and companionship while mitigating danger, unpredictability, the risks, and physical demands of live animals. So, with that background in mind, you're about to lay eyes upon the design that I created. But before you see that, you should know that this design has a few aspects to it. So first, there's the mechanical design. The mechanical design sought to maintain the flexibility and realistic locomotion of actual cats. And to minimize the amount of actuators in the system, a kinematic chain was developed to actually maintain this. Controllers and software used in this is the brand new Arduino UNO Q. And this is a very special microcontroller because it's also a computer. The new developments in microcontroller technology is basically cutting the middleman and creating a device that is capable of computing and running data acquisition and motor control. So these seem to be the future of control systems, and it is quite essential, in my opinion, for closed-loop systems. For this robotic cat, which we call Fhelix, Fhelix is going to need a few sensors and a lot of actuators. So the first kind of sensor is a LiDAR unit, which is a kind of distance measuring sensor. Next, we will use an orientation sensor, like a gyroscopic sensor, which is very common in Arduino technology. Then we use a microphone for voice commands and a motion sensor. The motion sensor is optional, but it gives the cat extra awareness if someone is ever approaching it. The robot will definitely need many motors, but we're specifically wanting servo motors for the 180-degree control accuracy and the high torque that they provide. Additionally, LEDs will be provided in the system just to add extra aesthetic and emotional feedback to owners as they're using the product. We know additionally that of course, that the system with all of the sensors and actuators, that's going to need a lot of power. And you'll see later on how much power it will probably require. So here we are. This is the work in progress model of the mechatronic system. Technically, this has no actual servo motors or sensors attached. You can imagine, though, what it might look like as a finished product from this design. And of course, I added my little star here just to give Fhelix some style here. And he's not only called Fhelix because of Fhelix the cat, but it's also because my grandfather was named Fhelix. So this cat has 4 legs, as usual cats do, and you can see that there's this rigid structure here, which is supposed to be the linkage. You can count right here. There's 1, 2, 3, 4, 5, 6. So this is a 6-bar linkage. And you'll see in a moment why we chose this and how it actually simplifies our control system. Right here, you can see there's a neck. It's actually 2 pieces of the same kind, but they're attached together. We'll flesh out why this is the case and how this is actually better for giving it a more expressive and realistic look to the kinematics of the design. You can see also that there is a controls box, but the model doesn't do any effort to flesh out what the controls will actually look like because that kind of knowledge is not relevant until the actual model is, the actual prototype is constructed. In the back, you could also see that there's a tail. So as before, as we had discussed, there are mechanical design features. The mechanical design is probably the most challenging aspect of this project that took place. But it was the most rewarding as well. It was a good experience. So to actually learn about how cats moved, I discovered that there was a research paper done by these scientists who were wondering how cats actually stabilize themselves. And they created this little model of how each joint moves and what the degrees of freedom are. And this diagram, along with a potential performance variable section, was actually very helpful in helping me to decide what kind of kinematic chain I needed to simplify the amount of actuators. Because we really had a choice. We had to choose between using 3. As you can see, there's 3 degrees of freedom here. 1 for the forefoot, 1 for the forearm, 1 for the upper arm. And the same for the back leg. 1 for the thigh, 1 for the shank, and 1 for the hind foot. You see, those are 3 degrees of freedom. But that would mean that there'd be at least 12 servo motors in the system, which is acceptable in modern electronics. But to save on costs, the method of linkage analysis could simplify the kinematic chain to reduce it to only 2 servo motors. So you'll see the 4-bar linkage uses a single driving link here. And all of the kinematic chains start with a 4-bar linkage. So this this linkage, which there's a kinematic diagram here, and we'll move through those actually in a bit, but these seek to merge this motion and this motion up here, and the same for this motion and this motion. And that was actually a major discovery in forming this linkage, that the back leg here is basically just a mirror image of the front leg. So the great thing about me making this was I was actually worried that I would need to create a linkage for the front leg and then make a whole new kind for the back leg, but I realized all I had to do was use the same one and just reverse it. So that's what you see over here. This is a mirror image of the linkage right here, and the parts are numbered, but that doesn't really help you right now. I'm about to show you what it looks like, though, in practice. So here is where all the magic is happening. Let me go to, I called it ready. But before that, you're going to see the kinematic diagram in motion. So here's the kinematic diagram. It looks like a lot, but once I start moving it, you'll see. Here is the forearm, or the, I don't know, the back leg called it the shank. And then we would call some portion of this the thigh, or the upper arm of the cat. And this type of motion can be used for the front and the back, as long as you just flip it to the other side. So here we go. That's just the initial. And these are construction lines. This construction line is for the driving link here, which is the only driving link. And this is the ground. And this is just another construction link, a construction line, but it is actually a real solid link that is necessary, but it's not closed so that the sketch doesn't become completely like this one. This is a 3-node link right here that was proven to be very necessary for this application. So you'll see in a second. The design is basically created so that the driving link up here can move all the way back there, and then it can, I'm sorry, it's not, oh man, hang on. Okay, so I think something changed when I pushed it back there, but that's the thing about this. What I don't want to happen is for this to go back here. So this ground link is basically the boundary line of the driving link, in my opinion. Because if I try to move this driving link past this way, it's going to break. And I fear doing that. So what is going to happen instead is that this driving link is going to stay over on this side of the motion. And so now you can visualize what's happening in the linkage here. This triangle link is very essential in being the connecting piece between this and this link here. But then the interesting development that occurred in creating this linkage was actually this one, where I realized it was quite a divine realization that if I just put something up here, then this would create some type of quick return mechanism. And it's designed this way so that if the cat is ever running, or if it's ever trying to walk really fast, then the servo doesn't really have to do much to move its arm that quickly. It can move in very small increments, and a lot of motion would be occurring down here. So now you're going to see in, let me close this before I go. Now you're going to see in the actual assembly of the link that I created, which has the same dimensions, what this would look like. So here we are. Yeah, it's just about the same, except you can't see any of the lines, and it actually looks like something instead of just a bunch of lines. And it's a lot easier to see it this way, but I wanted you to see what the kinematics of the structure looks like first. So again, this diamond piece was quite helpful in the overall scheme of things, but this one especially. You can see these are actually equal sizes here from there. So this is sort of like a linear actuator in a way. You see this one stays vertical for the entirety of the motion. So moving on to the hind feet and the forefoot, as you saw in the diagram, we developed this linkage so that we can combine these 2 degrees of freedom into one device that completes those kinematics using just one one actuator, a servo motor. But there's another degree of freedom still here, and that's important because we had a choice really to include it in the 6-bar linkage. But instead of doing that, I felt that this one should be its separate kind of actuator to, again, give it extra expression, power. It's going to be able to lift and raise its paw without needing to turn this thing, and that's going to make it feel more like an animal rather than a animatronic, in which this is quite animatronic, but with that separate servo on the forefoot, it's going to be able to do things that is less mechanical feeling. So for example, here's the assembly. All of the forefeet will be connected with servos. And just to note, you'll see back here we'll call this long leg, this long link right here, the end effector of the linkage. You'll see over here what I'm talking about. It has 4 holes here. That is actually a different length over here compared to the back, and that's intentional. You see the shank link here is a little longer than the forearm here, so I thought that I would show that in my design. So I made 2 holes in this here, and and so in the final design, it will be a different length depending on whether it's in the front or in the back. And Of course, if this was an actual manufacturing operation, we wouldn't have that extra hole in the bottom. We'd probably break it off or round it off right here, and this one would probably be fine. But you can see all of these are not really going in the same direction because it's not a mechanically decided um, operation right here. So you'll see what I meant before about expressions. So for example, the cat is sitting down, it's sitting upright, you would say, and the arm is going down there, the feet are down, this is its sitting position. But then it raises its arm a little bit so that it could say hello, or you can give it a high five. And so we're going to have like touch sensors and certain other things in there so that it can give you feedback, sort of like a person would, but in a cat way. And so in doing this, there's going to be extra stability involved in the design as well, because it's going to be able to correct all of its motions as it moves. So you can see it looks pretty agile. And this would not be possible with a, it would be possible with a mechanical structure, but it wouldn't look so lifelike if everything was moving exactly the same over and over and over and over as the operation continued. It would just look mechanical. So to minimize that risk of mechanical looks, this is what I decided to do instead. The neck is an exciting feature of this robot because it includes 3 servo motors, one to pivot it at the bottom, one that sits upright and pivots it in this direction. As you can see, I'm going to refer heavily to the, I drew these as I took a screenshot. These arrows are the axis of rotation, and all of them, this line of rotation is perpendicular to these two, like perfectly perpendicular. And then these ones, of course, if this one rotates, then they'll be off. They won't be parallel any longer. But the reason this was necessary was that initially the design was only going to be these 2 servos. It was going to rotate at the top like that, or actually, it was going to rotate at the bottom like this, at the base. So imagine it just rotating at the bottom there, and then the head would move up and down, nodding up and down. But soon in integrating this design, it did not look lifelike. And I realized that the neck has a lot more pivots than we realized. This might even be missing a 4th joint, which is a side-to-side bobbing, where you would see that we're able to move our neck in all sorts of positions, and this doesn't even cover all of them, but it does cover a good amount. And you'll see that with it being able to put its neck up and down this way for it to be able to rotate in this direction here as I'm following with my clicker there, it looks pretty lifelike. It, it having a neck in general is necessary because it wouldn't be able to look animalistic in that way, because animals have necks, and without the neck, it would look even more like a robot. So the final mechanical feature to consider is this tail feature and the housing. Now, of course, you can tell right away this is AI, but I'll get to that in a second. So the tail is going to be directly in contact with a servo motor, and the tail will be a very light material, maybe like plastic, something like that, so that it would effortlessly move through rotations and move to where you want it to be quickly, kind of like an actual cat. But it is just a long pole, and it will, for safety reasons, be slack most of the time, so that when there's children playing, that it doesn't poke anything on them and get them hurt, because that's the last thing we want. This robot would not be a good design or a necessary one if it's going to get people hurt. And finally, the housing is a really exciting and challenging feature of this, because in order to get it to look as perfect as this picture, we're going to have to create something that actually covers up all of these aspects of the design. And that's not impossible. It's not impossible, but it's going to have to be good, and it's going to have to be lightweight. Some form of plastic is ideal, and then the outer shell, of course, you can see it's some sort of polyester. This is exactly what I'm hoping the final product to look like. Moving on to sensors, the sensors are this combination of vision sensors, audio sensors, and touch and motion, well, let's say orientation sensors. There's a lot that could be said about these, but there's a lot that's already been said. I would say that LiDAR is included, and cameras, so that object recognition can be available in the system. And then the microphone will be available so that you can give the cat the preset commands, like telling it to come here, or to sit down, or to go to sleep, kind of things. Touch sensors will be implemented on the face, and possibly pause, just so that when it comes into close contact, that it knows that it's actually in close contact. Sort of like a failsafe, because the vision system is competent, but not always the best to rely on. And the orientation sensor will just be there so that the robot will know how to position the rest of its body, the center mass. And this is usually necessary in roaming robots and in robots with limbs. And in a home and dynamic setting, this is necessary so that if there's any obstacles, it'll be able to know how to position itself. As we had mentioned before, there's going to be many actuators. There's going to be 12 servo motors, and there's going to need to be at least 4 of them to drive the linkages. There's 4 linkages, so we need to find some considerably strong and high torque servos for those applications. The paws, and I'll just go back so you know what I mean, the paws here are going to either need a high torque I would say a high torque servo motor is necessary since it's going to be handling all of the weight of the robot on its own down here. Of course, it's going to be helped by the other feet, but there are moments where, like in this position here, there's a considerable amount of force going on here. And so we would ideally want there to be at least 8 high torque servos, and then the rest of them can be lighter torque, like for the neck, because the neck is not going to have much weight at all. And then the tail. The tail over here is really light, so we would have really low torque servos. The speaker, of course, we'll have a speaker that's going to play little sounds that will aid in getting any communication across between the user and the robot. There'll be songs, there'll be cat noises, and all sorts of things that would help the user know what kind of state that the system is in. And also to make it a more enjoyable experience, because to make a silent robot like this, animals aren't really silent. And to enhance the experience, this kind of speaker system could help the robot feel more lively. LEDs will also be included in Fhelix so that the colors and the lights will help it feel like a robot, yes, but also to be more friendly seeming, have more a higher way to communicate and respond to things than just sounds and motions. It will have these lights that will show how it's feeling. Lastly, there's going to be these actuator bevel gears that will turn the rotation of the servo motors 90 degrees. And this is a consideration due to the lack of space that is in the housing here. I say the chassis, this gray part, this large gray part. There's not much space in there, and you can imagine that a servo motor would not really fit in this kind of space. So the solution for this would be to turn it vertically upwards and make the rotation go this way, about this axis right here. And this will be the driver of the linkages here, and this should help maximize the amount of space that is given here, given that the controls are here. Of course, this housing is not the final draft, and there may be more space, but this kind of system can actually help in minimizing the amount of space that is used inside of the housing, so maybe even further optimizations can be made. Next, we have the power requirements, and there's quite a bit of power in this robot. I'll be pretty brief on this section. It's 12 motors, 1 LiDAR sensor, an orientation sensor, microphone, speaker, and touch sensors. All of them are 5-volt ratings, and all of them have different numbers, and that leads to nearly 100 volts for the system. So we would get a high voltage battery for the system, but we would allocate them to different sections. So we would need, if we were going off of 9-volt batteries, which is the most available power system, we would allocate 8 to the motors over here. And I'll talk about what this is in a second, but this is a motor shield. In the controller board here, this receives 2 batteries. It doesn't really need much to operate, and all the sensors are pretty low power, and there's not that many of them either. The speaker will be attached to this motor shield, so it will have a significant amount of power available. So like I said, there's going to be a controller. It's going to be a closed loop operation. The Arduino UNO, which is this device right here, is a computer and a microcontroller. You can see that there's a microcontroller chip and a computer chip on here. On this version, I can't tell whether it's 4 gigs or 2 gigs of RAM, but the fact that it's that high makes it great for big data. And in this kind of operation with LiDAR, what we're seeking to do is to run a SLAM program, which means simultaneous localization and mapping. SLAM is pretty much the gathering of LiDAR data and building a map, as shown in this figure here. And it's used in a lot of surveying, and robots use it so that they could run a closed loop system that is able to gather data from the surrounding environment and make choices based off of that, depending on its operation. And in this case, the cat is going to use it to recognize who's around them and to recognize what to avoid in its surroundings, and maybe whether to speed up, whether to slow down when it's moving, and possibly where to rest when it's time to start charging. And like I said, there's a motor shield. This motor shield expands the capacity of the Arduino UNO, and it can allow up to 16 motors on here. You can see there's 16 pinholes. Thankfully, we don't need 16. We have 12, which is still insane to think about. But we're not going to be using all 12. We're also going to be hooking up the speaker and LEDs to the same system. And that's just so that we can be able to keep all of the output actuators onto this one board here. But technically, we still have this. There's pins on the Arduino that we can use for the speaker and LEDs. But if we wanted to, we can hook it up here. So now that you've seen the entire design, I want to reflect on it and see what kind of improvements, what kind of problems I might see in the future for this design, and the kind of things that I like about the design that I wouldn't want to change. So first, the improvements I thought about right away were the kind of servo motors that I sought to use. The kind of servo motors I was thinking of using were not like these, but it kind of popped into my mind that flat servo motors might do the job if we want to keep the robot in a small, thin look like this, rather than sticking a very chunky servo motor on the side right here and just ruining the thin contour of this design. We could probably use a flat servo motor and bolt it to the side, and this would not take up much space and it could be hidden in the housing quite well. The only issue is that it might cost more, but we never know. And next, I was thinking maybe some springy features could be used in it, but I had no way to verify whether they would assist in the kinematics of the robot or just make the system more chaotic. And in my mind, I'm thinking it might be more chaotic because if you have uncontrolled oscillations in this locomotion, that only hinders the stability of the system. But if you have complete control over the driving link here and of the limb over here, this paw, and you have it driving perfectly fine, I think the only thing you would need a spring for is to really make sure that the parts are actually staying in place. And what I mean is that some of the parts on here could like get stuck. So like if this link decided to go back over there, maybe we would want to put something over here so that it doesn't cross this threshold or that threshold. Because this, as I had mentioned before, this link should not be going past over here. This should not be going over here at all. Is the linkage accurate? Yes, it is quite accurate. Is there anything missing? Yes, I would say that the model doesn't have that many sensors, and that's possibly an issue because if the robot ends up just relying on the LiDAR and only the few touch sensors, it may not be as accurate as we hoped. And what issues might arise is possibly in the locomotion and also in the SLAM technology. The SLAM technology needs to be able to be updated. If the updating doesn't happen, then it doesn't realize that there's dynamic situations going on in its environment. So it needs to be able to update. If it doesn't update, someone can come right in front of it and it won't even know because it only has data from what the room looked like before the person stepped in the room. So I'm satisfied with the design, and I like the Arduino UNO Q as a good controller because it provides the computer and the microcontroller in one package, bringing a complex system down to one down to one device. And I like SLAM as a program because there's not many other options that are as versatile as this for a closed system. And the local AI that will assist in voice commands, I think this will be a very neat feature that will help Fhelix to feel like an actual cat.